Electrostatics. Means this is charge, and statics means it is at rest.
Yes, sir.
Okay, so electrostatics in this chapter we discuss when the charge is at rest. Now we have two concepts in this. One is electric field, field, and other one is electric potential. Electric
Potential.
potential. And then you see electrostatics means the charge is at rest. Okay, this is divided into two parts, electric field and electric potential. Now, if the charge is at rest, if the charge is moving, then we call it as current electricity.
Yes, sir.
Okay, when the charge is
Moving.
when it is moving, then it is current
Current
electricity.
electricity. Yes,
Okay,
sir.
when it is at rest, then it is electrostatics. Now we discuss about the charge.
Yes,
Okay,
sir.
what is an electric charge? What is an electric charge? Okay, charge is a property. It's a property associated with the matter. Charge is a property associated with matter. Associated with matter, due to which due to which it produces due to which it produces and and uh, experiences electrical and magnetic effects.
Yes, sir.
Electrical and
Magnetic
magnetic
effect.
effects. Okay. Now
Yes, sir.
this charge can be produced by friction. Say for example, now every body is if you take a body, then it is neutral. Okay, it is
Yes, sir.
neutral. Okay. So now if you can remove the electrons, if you remove electrons, then it becomes, as it lost electrons, there were more number of positive charged
Charge.
particles than electrons. So that's why we say it is
Charged.
positively charged.
Yes, sir.
If you remove electrons, if you're not removing electrons, then number of electrons is equal to number of neutrons, number of protons, so it is neutral.
Neutral charge. Yes,
Okay,
sir.
now you take a glass rod, a glass rod you take a glass rod. Okay, you take a glass rod and rub it with a silk cloth.
Yes, sir.
Rub it with a silk cloth. Now, if you glass rod is rubbed with silk cloth, then this silk cloth removes electrons. Removes electrons. That means it acquires electrons. When it acquires electrons, then we say more electrons here. So we say it is
Negatively charged.
negatively charged.
Yes, sir.
As it lost electron, the glass rod lost electron. As it lost electrons, we call the glass rod as positively
Positively charged.
charged.
Yes, sir.
So this electrification, I mean, making it positive or negative, we have done by using friction. By
Yes, sir.
using
Friction.
friction. So we can induce charge by friction. So this
Friction.
is
Yes,
one method to produce charges. Okay.
yes, sir.
The other method is you take a you take a you take a neutral body. Okay, now place it on a insulating stand,
Yes, sir.
and you take a glass rod, rub it with a glass rod, and rub it with silk cloth.
Yes,
Then
sir.
silk acquires negatively charged, and this acquires positively
Positive.
charged. Then this positively charged glass rod, you keep that in contact with with the the metal sphere placed on an
Yes,
insulating stand. Then
yes,
this
sir.
acquires some positive
Positive charge.
charge. So this is called as charging by conduction.
Yes, sir.
Charging by conduction.
Conduction.
Okay. Now you take this metal sphere, place it on a insulating stand,
Yes,
and take a charged glass rod. I mean positive glass rod.
yes, sir.
Okay, so then it attracts electrons on this side. Okay, and
Yes,
repels positive charge on this side. Now you connect it to the ground. When you connect it to the ground, all this positive charge will go to the earth, because
sir.
because this positive will repel positive and attract
Yes,
the
sir.
negative.
Negative. Yes, sir.
Later you remove the connection. When you remove the connection, the metal rod will have
Negative charges.
negative charge. This is
Yes,
called as charging by charging by induction.
yes, sir.
Okay, this is charging by conduction.
Conduction.
This is charging
Friction.
by friction.
Yes, sir.
Okay. Okay. So
Yes,
now first of all we discuss about a point charge. Okay. Right. Now next one is quantization of charge. What do you mean by quantization of charge? This quantization of
charge.
charge. Okay,
Yes,
charge will exist like Q is equal to NE.
and need.
That means Q is n times of E, where
Yes,
n can take values like 1, 2, 3, so on. Okay, so you can remove one electron or two electron or three electron.
yes, sir.
So, right, so okay, so you
Yes,
can n into multiple of electron charge.
yes, sir.
Okay, n into multiple of electron charge. That the charge is quantized. Okay,
Yes,
so n into electron charge. Okay, so if it is having more electrons, then we say it is negatively charged.
yes, sir.
When it is you're having less electrons, then we say it is positively
Positive
charged.
charge.
Okay, then
Yes,
charge is always associated with another point to note is charge is always associated with mass.
yes, sir.
Always associated with mass.
Oh,
So if it loses electrons, that means its mass
mm,
decreases.
yes, sir.
Okay.
Mass increases, sir.
How it will increase? You are losing some charges. You are losing some mass, right? It will have mass. Electron has some mass, right? So if it is
Yes,
losing
sir.
electrons, then obviously
It
it is
will
losing
decrease the
some
mass. Mass,
hmm,
yes, sir.
mass will be reduced.
Yes, sir.
Okay. And charge can neither be created
Be destroyed.
nor destroyed. Okay, that is charge is conserved.
Yes, sir.
Charge can neither be created nor
Destroyed.
destroyed. Charge is always
Conserved.
conserved. Charge is always associated with mass, and
Yes,
charge is
con-
quantized.
yes, sir.
Okay.
Con-
charge resides on the surface of the conductor. These are all characteristics of the charge.
Yes, sir.
Okay, charge resides on the surface of the conductor. Charge resides on the surface of the conductor. Now you take a metal solid metallic sphere and give some charge, then it spreads out and will, because of repulsion,
Yes, sir.
and it will always come on the surface.
Surface.
Charge
Yes,
resides only on the surface.
yes, sir.
Okay, right. Okay, Q is equal to Ne, quantization of charge. Charge
Charge.
resides on the surface of the
Conductor.
conductor. Right. So you can charge a body by friction,
Friction.
by conduction,
Conduct.
by
Conduct.
induction.
Yes, sir.
Okay. Now, then we write Coulomb's law. Coulomb's law. Coulombs. Coulomb's law.
Yes, sir.
What is Coulomb's law? Now you take two charges. Say here charge is Q1 and Q2.
Yes,
Okay. The
yes.
distance between them, is R.
R. Yes, sir.
Then the force of attraction, or repulsion. Say if they are both are positive, if
Yes, sir.
both are positive, then you will have
Pulsion.
repulsion. If one is positive, other one is negative, they will have attraction.
Attraction.
This force F is directly proportional to Q1, Q2. Okay, I have written small q, so I will write here Q1 and
Q2.
Q2. Okay, now
Yes, sir.
regardless of whether they are having positive charge or negative charge, you put them in modulus.
Yes,
Okay,
sir.
Q1, Q2 by
R
R
square.
square into K.
K.
Okay, so this force F is equal to 1 by
4 pi
4
epsilon
pi
naught.
epsilon naught, which is constant because force
Yes,
is directly proportional to Q1, Q2.
yes, sir. Q1, Q2
Q1,
by.
Q2. Now, every time I'm not writing this modulus,
Yes, sir.
okay, I'll just write the Q1, Q2, but you have to remember that this is modulus. So it is
Yes.
having negative charge also, you have to write positive only. 1 by
Okay.
4 pi epsilon naught Q1, Q2 by R square, where R is the distance from their centers.
Yes, sir.
Okay, this 1 by 4 pi epsilon naught value is 1 by 4 pi epsilon naught value is 9 into 10 power 9.
Yes, sir.
9 into 10 power 9 Newton meter square by Coulomb square. Okay, that is a
Yes, sir.
value of 1 by 4 pi
Epsilon
epsilon
naught.
naught. Okay, so epsilon naught is the
Free space.
permittivity of free space.
Yes, sir.
This is the permittivity of free
Free
space.
space. Yes,
Okay,
sir.
right. And this epsilon naught value is 8.85 into 10 power minus 12 Coulomb square by Newton meter square. Okay,
Yes, sir.
right. So, right. Now, if you want to write this in vector form, then it is F is equal to 1 by 4 pi
1 pi
epsilon naught Q1 Q2
Yes.
by R cube into R bar.
Yes, sir.
Okay, this is a vector form.
Yes, sir.
Vector form of Coulomb's law. Okay, now
Yes.
here from here you can write many formulas, which this formula actually gives you the force. Okay, force between two charges separated by distance r. Now, if Q1, Q2 are same, then F is inversely proportional to R square.
R
So the
square.
question will be like this. Say there were two charges,
Yes, sir.
Q1, Q2. Initially the distance is R. Now the distance is, now initially the distance is R1. Now the distance is R2. Same charges, Q1
Yes,
and
sir.
Q2. Then what is the force now?
Four.
Then,
Yes.
then here Q1, Q2 are constant, K is constant. So F is inversely proportional to R square. So F1 by F2
Equal.
is equal
R
to
two by
R2
square.
square
R1.
by
R1
R1 square.
square. Yes, sir.
Okay.
Yes,
This
sir.
is this is one model which you need to remember application.
Yes.
Okay. Okay. Right. Then we'll discuss some applications how to apply Coulomb's law. This is for point charges. So if you
Yes.
have 2 point charges, then how to calculate the force. Okay. Now, if sometimes he will give you a question, application 2, he will give you a question that um, these uh, this there are two charges. This is Q1 and this is Q2,
Q2.
and we have touched this one and kept here. See, both were touched. Then we write Q1 plus Q2 by 2. Now,
Yes,
if you
sir.
touch this one, this will become Q1 plus
1
Q2
plus
by
Q2
2.
by 2.
Okay, now here the force, here the distances are again they kept at the same distance. Then F1 is equal to K Q1 Q2 by R square. Here you will write F2 is equal to K into
Q1
Q1
Q2
plus
by
Q2 whole square, right? Q1 plus Q2 by 2.
yes, sir.
So Q1 plus Q2 by 2, Q1 plus Q2 by 2
Whole square.
whole square by
R.
R square.
Yes, sir.
Okay, equation 1 by equation 2
Yes, sir.
will give you the value of F2. Okay,
Yes, sir.
now
Yes.
now we will do another model. He might be asking you a question like this. Say there were charges kept in form of a triangle. Then what is the force on this? Let's say this is force on A. Let us take this as B, this as C. And what is the force on B? Now let us take that this is plus Q1 and this is Q2 and this is Q3.
Q3.
What is the charge on A? Okay.
Yes, sir.
Now you can see that the force between these two will push in this direction. Okay. Now the charges form an equilateral triangle. The question you will say the charges form an equilateral
Triangle.
triangle.
Yes, sir.
Forms an equilateral triangle. This is going to push in this direction. Let us call this as F. This is going to push in this direction.
Yes, sir.
Okay, because this is F1. Let us call this
Yes.
as F2.
Yes,
Okay,
sir.
now it forms an equilateral triangle. So if it is R is the distance here, R is the distance here because that's an equilateral. So we are calculating the net force here. The net force F net will be equal to, now here equilateral, so here the angle is 60. So this
Yes.
is a straight line.
Yes, sir.
Okay. Now this is a straight line, or this is a straight line. So the angle is one. This angle is total angle is 180.
180. Yes, sir.
So this angle is 120.
120. Yes, sir.
Now you see this is a straight line. If this is 60, this is 120. So this should be 60.
60. Yes, sir.
Because this is a straight line. So this
Yes,
is total angle is 180.
yes, sir.
So this angle should be equal to 60 because 60 plus
60. Yes,
120 gives you
180.
180. So the
Yes,
angle between F1 and F2 is 60. So as force is a vector, you have to add it vectorially. So
yes,
F
sir.
is equal to F1
F1
plus
plus F2.
AF2. Now this is also called as principle of superposition principle or principle of superposition. Okay,
Yes,
it just tells you that if they are vectors, you have to add them vectorially. Okay,
yes, sir.
so the formula will become
Yes,
the resultant force F net will become root of F1 square plus F2 square plus 2
2
F1
F1 F2
F2
cost.
cos theta.
Yes,
Now
sir.
here you can substitute theta is equal to
60.
60 degrees here.
Yes, sir.
Okay. Now sometimes he will give you another application we will discuss. So the same model we can use it for fields also. Same method we go for fields also. Okay. So now
Yes,
here two charges will be there.
sir.
Now here the charges Q and Q. Okay.
Sir,
Yeah.
ఏ చార్జ్ అయితే అడుగుతున్నారో ఆ సైడ్ కి డైరెక్షన్ పుల్ అవుతుందా సార్?
No, no. It's all about how are the charges. Say for example, now here this is plus Q1.
ఎస్
Okay.
సార్.
So then this this is positive. This is positive. So that's
ఎస్
why
సార్.
it is repelling in this direction.
సో
This
వై
is
నాట్ ఇన్ దిస్
positive. This
డైరెక్షన్?
is a charge always pushes in opposite direction. Positive and positive will repel.
ఎస్ సార్.
Straight line will act
ఎస్
in straight line. The charges will act in straight line. So it will repel in this direction. Now
ఎస్
as
సార్.
these two charges are equal,
ఎస్
so
సార్.
this will become F. This also becomes
ఎఫ్.
F.
ఎస్
And
సార్.
this is theta. Then this
ఎస్.
also becomes theta as we have learned from here.
ఎస్
Then
సార్.
F net is equal to root of F square plus F square because the charges are same and the distance is also same because this is equilateral.
ఎస్
So
సార్.
f square plus 2 f
2
square
కాస్ట్
cos
థీటా.
theta. See, many of the times I will be using this as a shortcut. Listen carefully. F square plus f square is 2f square.
ఎస్ సార్.
2f square plus 2f square cos theta. So
ఎస్.
that gives me root of 2f square into 1 plus cos theta. Then 1 plus root of 2f square. This is 2 cos square theta by 2. 1 plus
ఎస్.
cos theta is 2 cos square theta by 2. That is
ఎస్.
equal to root of 4 f square cos square
థీటా
theta
బై
by 2. That is equal to
2.
2f cos theta by 2.
2. ఎస్
So
సార్.
this is used as a shortcut. If the forces are equal, then I'm going to write 2f cos theta by 2 directly,
ఎస్ సార్.
where theta is the angle. So if it is equilateral, I'm going to substitute 60 by 2, 30 I'm going to use.
ఎస్
Okay.
సార్.
So application 4.
5 సార్.
Sometimes, yeah, 5. So sometimes if you get like this, say same thing, Q, Q. Here what I'll do is this, I will do it as minus Q. This is plus Q. Then here this Q will attract in this direction. This force
ఎస్
is
సార్.
F. This will repel. This will repel in this direction.
ఎస్ సార్.
Okay. So here the angle is 120
ఎస్ సార్.
and this force is F. Okay. This force is F. This force is F and the angle between them is 120.
120.
So I will get F net is equal to 2f cos theta by 2. Here theta is 120. You have to see whether it is attracting or repelling.
Yes, sir.
Okay. Right. So that's about the charges.
Yes.
Okay. So net force you have to calculate. Okay. And the another model. What you can do is you have charges like this. Okay. So now these were the charges. So let us take this one as plus q.
Yes, sir.
This is plus q, and this is plus q, and this is also plus q, and this one also plus q.
Yes, sir.
Then what is the force acting here? Okay. Now this is a square. Okay, equal charges q placed on the four corners of a
Square.
square of side A. This side is A.
Yes, sir.
So now we have to calculate, okay, the net force. Now here
Yes.
this plus q will push in this
Repel. Yes,
direction.
yes, sir.
Okay. Now this is force due to C. I will call this as C. This as D. This as
A.
A, and this as B.
B.
Okay, FC will act in this direction.
Yes, sir.
This A will push it in this direction because it is positive. So this
A.
is F
A.
A.
Yes, sir.
Okay, then this D will push this one in this direction.
Yes, sir.
That is FD. Now you
Yes.
have to add them vectorially. F net is equal to F net is equal to, now as you can see, FC and FA are perpendicular to each other. So
Yes.
I will write root of perpendicular vectors, root of FA square plus FC square plus 2 FA FC cos 90. Cos 90 term will become 0.
Yes, sir.
So we write FC square plus
F. A. Square.
FA square plus
F. D.
FD.
Yes, sir.
And you have to remember that FE, FC and FA will be same actually,
Yes, sir.
right?
Yes, sir.
The FC is equal
Is
to
F.
FA
A.
magnitude wise.
Yes.
That is KQ square by A square.
Yes, yes, sir.
But whereas this BD, this FD will be different. FD is equal to, now this is A, this is A. That means this distance is root 2A. I will
Yes, sir.
use Pythagoras theorem.
Pythagoras theorem. Yes,
Okay.
sir.
Now this is equal to root of A square plus A square, that is equal to root of 2A square, that is root 2 into A. So
Yes,
it
sir.
will become KQ square by
Root
root
2A.
2 into A.
A. Yes, sir.
So just substitute here, then we will get the value of
F net.
F net.
Yes, sir.
Okay.
Yes, sir.
Right. Now we'll discuss electric field. Electric field. Now, what is electric field? See, if you have a charge, then this charge produces some field.
Yes, sir.
Okay. The space around the charge where its influence is felt is called as electric field. Say if I bring one unit positive charge here, if it is repelling, then that is inside the field. If I place it outside, if I place a positive charge outside and if it is not repelling, then we say this is out of the
Out
electric
of the
field,
electric. Yes, sir.
right? So electric field, the space around the charge where its influence is felt,
And yes, sir.
the space around the charge. Three-dimensionally, you have to imagine the
Yes,
space
sir.
around the charge
Where it's influence.
where its
Influence is felt.
influence is felt
Yes, sir.
is called
Electric field.
is called
Electric field.
electric field. Okay. Now,
Yes,
electric field at any point is defined as the force acting per unit charge.
yes, sir.
Electric field is defined as the force acting per unit
Charge.
charge. Okay. So now E is equal to F by Q
Q
naught.
no.
So that is Newton. Unit is
Coulomb.
Newton per coulomb.
Yes, sir.
Okay. Now electric field is a vector quantity. Is a vector quantity. Electric field is a vector quantity. See the arrow mark on the head.
Yes,
Okay.
sir.
The force acting per unit charge is called as electric field.
Electric
Okay.
field.
The direction of force is the direction of
Electric field.
electric field.
Yes, sir.
Okay. So here also electric field also same concept we will apply for the electric field. Superposition principle is applicable here.
Yes,
E1 plus
E2.
E2 plus so on. Okay.
Yes,
This is principle of superposition.
superposition.
Same as that of forces, because
Yes,
electric field is also a vector. Now the
yes,
same questions in terms of electric field I can write. Say for example, if you have charges like Q and Q, then this is going to push in this direction, this is going to push in this direction. Now here I will write
E1,
E1
E2,
and E2, and let's say if it is an
E2,
equilateral, then E1 will be equal to E2.
E2. Yes,
Okay.
sir.
Then we write
Root of
E is equal to root of E1
E1
square
square
plus
plus
E2
E2
square plus 2
2 E1
E1
E2
E2
cos
cos
theta. Theta.
theta.
Yes,
Now
sir.
here in this case, if I take Q and Q,
Yes,
then now I will get E1 is equal to E2
sir.
magnitude wise.
Yes, sir.
Then I will get E net is equal to 2E
2E cos
cos
theta by
theta
2.
by
2. Yes, sir.
2E cos theta by 2.
2.
The same thing like if you have four charges on the square, then this we call this as D, this is A, this is C, this is B. All positive charges if you keep plus Q, plus Q and plus Q. This is going to push in this direction. This is FC.
Yes,
This
sir.
is going to push
FA,
in this direction, FA, and this is going to push
FD.
in this direction, FD.
Yes.
And the net force is equal to root of
Sir, that is E no, sir. Actually, you're writing F.
uh,
E.
FD, FC, FA, FC, and this is due
Electric
to
field
FD.
E, sir.
This is electric field. E net
Yes.
is equal to, sorry. here
Yes.
EC, ED, EA. Okay,
Okay.
now the electric field is F by Q naught. So I'll be writing 1 by 4 pi epsilon naught into Q by R square.
R square.
So Q by R square. Okay, now so
Yes, sir.
this one, this Q plus Q
Yes, sir.
is having this distance
Represent
is root 2
root
A.
2a. Yes, sir.
Okay, so
E
now here E A square plus E
E
C
C square.
square plus
E D.
E D,
Yes, sir.
and E A will be equal to
Equal E
E
C
C is equal to K
K Q
Q
by
square
square
K
by
Q
R.
square, K Q by
K Q by R square.
K Q by R
R
square.
square.
Okay.
Yes, sir.
Now if this side is A, then A square.
Yes,
So,
sir.
and ED will be equal to KQ by root 2A
O whole
whole
square.
square. Okay, we have to
Yes,
just
sir.
substitute in this. Okay,
Yes, sir.
so we get electric field.
Electric field.
Okay, this is electric field due to point charge. So if you have a point charge, then this is how you are going to get a electric field.
Field. Yes, sir.
Okay, now electric field due to continuous charge distribution. When we study about continuous charge distribution, electric field, electric field due to due to
Con-
continuous charge distribution. Now, when you take electric field due to continuous charge distribution, before that uh, we have to understand few concepts. One is linear charge distribution.
yes.
Okay, so what is continuous charge distribution? Continuous charge distribution means earlier I took only point charge. Now
Yes,
I
sir.
am taking a rod. I'm considering a rod, and for that rod, it is having a charge Q now.
Yes, sir.
Now here, this is not a point charge. This is an extended body. So for
Yes, sir.
extended body, we are calculating electric field. Okay,
Yes, sir.
the length is L, Q is charge, and length is L. Then we have something called as linear charge density. Later we'll discuss what is electric field for these things.
Yes, sir.
Linear charge density. So base concepts first. Linear charge density. Linear charge density is linear charge density is Q by length,
Yes, sir.
charge per unit length. Okay, this is in coulomb and this is in
Meter.
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 So coulomb meter inverse is SI unit for linear charge density.
Yes.
And
Yes.
this linear charge density I am writing on denoting with lambda. Lambda is equal to Q by
Q
L.
by L. Yes, sir.
And then this is linear charge density. Then linear charge density. Then we discuss surface charge density. Surface charge
Density.
density. In surface charge density is denoted by
Sigma.
by sigma.
Sigma.
Sigma. Sigma is equal to charge per unit area.
Area. Yes, sir.
Charge per unit area. So we write this as this is coulomb. Area is
Meter
meter
square.
square. Coulomb
Yes.
per
Meter
meter
square.
square is surface charge.
Density.
density. Then comes
Volume, charge density.
volume charge density. Now the volume charge density is rho. Rho
O
is
S
equal to
Q by
Q by V.
V.
That is Coulomb
Coulomb
per
meter
meter
cube.
cube.
Cube. Yes, sir.
Okay. This Coulomb per
Meter
meter
cube.
cube. Okay.
Yes.
Right. Coulomb per meter cube. Now, for we will discuss about continuous charge distribution.
Yes, sir.
Continuous charge distribution. Okay. So I will take a line charge and then I will write the formulas for it. Okay.
Yes, sir.
So now if you take a line of charge, so line charge, surface charge density and volume charge density. Now I will write this electric field, electric field, electric field due to a
Line.
line charge. Okay.
Yes, sir.
Later I'll prove this one with Gauss law because that will
Yes,
be easier. Okay. As of now, I'll just write the formula for this.
yes, sir.
Okay. So now if you have a straight uh, conductor which is having some charge Q
Yes.
and length L, then its charge density will become lambda.
If
Then
it,
E net is equal to the net electric field is equal
yes, sir.
to lambda by 2 pi epsilon naught R.
Yes, sir.
That is the net field. E net for line
Line
charge.
charge.
Lambda by 2 pi epsilon naught
Epsilon naught R.
R.
Yes, sir.
Then then next one is charged circular ring. Electric field due to short circular ring. Electric field due to short circular ring. Now if you have a circular ring,
Yes, sir.
now its radius is R. On the axis at a distance x,
Yes, sir.
now it is having a charge q.
Yes, sir.
The circle is having a charge, this ring is having a charge, circular ring is having a charge q. Now at x distance we are finding the electric field. Okay.
Yes, sir.
So now at electric field here at some distance x is now k q x by, or electric field is equal to kqx by r square plus x square whole power 3 by 2.
2. Yes, sir.
The electric field is equal to kqx by r square plus x square whole power 3 by 2. Or else I can write E is equal to k is 1 by
4.
4 pi
Epsilon naught
epsilon naught
QX
qx by r square plus
X
x
square.
square whole
3 by
power
2. 3 by 2.
3 by 2. That is electric field due to
Short circular ring.
short circular ring
Yes.
or electric field due to just right circular ring.
Ring. Yes, sir.
Okay.
Yes, sir.
Now x is the distance from the center of this one.
Center.
Okay.
Yes.
Now at the center, the electric field at the center is equal to how much it will be? Now if you put x is equal to 0, then you will get at the center. At the
Yes, sir.
center, it is equal to 0, because if you put x is equal to 0, if you put
Yes,
x is
sir.
equal to 0, here x is equal to 0, then this term will become
Everything
0.
0.
So
Yes, sir.
you will the field at the center will
Field of
become
center.
0.
0.
And also you can see that at the center, now if you are having positive charge here, positive charge here, then it is pulled in this direction the same way it is pulled in this direction. Now here also you have charge, uh, say pushed, or rather you can say just to want to visualize, then here positive, this is positive, so
Yes,
this
sir.
positive charge pushes in this direction, this positive will push in this direction,
Yes,
both are
sir.
having same magnitude, opposite direction, so they will cancel out. So
Cancel it. Yes, sir.
here also you will have charges. Okay, so this will push in this direction, this will push in this direction, so like that every side there is a charge
Cancel.
on the other side which cancels.
Yes,
So
sir.
the net field will be equal to 0 at
0.
the center of the circular ring.
Ring. Yes, sir.
Okay, so these formulas we need to remember. You write it in a separate notes, and then all the formulas you have to
Yes,
write
sir.
and learn. Okay,
Yes, sir.
now the infinite sheet of charge. So if you have an infinite sheet of charge, then infinite infinite sheet of charge. So if you have an infinite sheet of charge, say that's an infinite sheet of charge, and you're having positive charge over here,
Yes, sir.
then the electric field E is equal to sigma by 2 epsilon naught.
Yes, sir.
Electric field is equal to sigma by
2
2
epsilon.
2 epsilon naught. Okay,
Yes, sir.
so yeah, you just note down these formulas. Later in after Gauss law, we will discuss the
Yes, sir.
values. Okay.
Yes, sir.
All right. Uniformly charged spherical ring. Okay. Uniformly charged spherical ring. Charged spherical ring. So there is a ring here which is having positive charge. Then at the center, whose radius is r, we have to calculate the electric field. The electric field at the center, the net electric field is equal to 2k lambda by r. That is equal to k is 1 by 4 pi epsilon naught. So 2 2
Lambda.
into lambda is q.
Yes,
Lambda is q by k is 4 pi
R.
epsilon naught
R.
by, yeah. So this is what this is pi r. This
Yes,
length is pi r. So lambda is q by L. L is pi r.
Yes,
So
sir.
two times. So we get this as q by 2 pi square
Epsilon naught
epsilon naught
R.
r square.
Yes, sir.
Now 4 pi epsilon naught. Now already one r is there, na? So you will get r square. Here
Yes,
one
sir.
r is there, so you will get r square. So this is a net electric field due to the charged
Spherical
spher-
ring.
spherical
Ring.
ring.
Yes.
Okay.
The center
Now,
zero ఉంటుంది, sir.
no, we will have net resultant because this one will push in this direction, this one will push in this direction, this one will push in this direction. So net, if it is a circle, then it
Yes,
will
sir.
be 0, but it is not a circle, it is only half of the circle, semicircle.
Yes.
So you won't get 0.
Yes.
Semicircular ring charged, semicircular charged, semicircular, not spherical, semicircular ring. Okay,
Yes, sir.
right. Then, right, uniformly charged disk. So there is a disk here, x distance, radius is r.
Yes, sir.
At this point, now it has got sigma is the surface charge density,
Yes.
then E is equal to sigma
Now
by
by
2
2
epsilon naught
epsilon naught.
into 1 minus x by root of x square plus r
R
square.
square.
That is the
Yes.
electric field for the disk.
Yes, sir.
Okay, now I want you to remember this one, most important,
Yes, sir.
and infinite sheet of charge
Yes, sir.
and ring and electric field due to
Line
line
charge.
of charge.
Yes, sir.
Okay, remaining we will derive after Gauss law.
Gauss. Yes, sir.
So for the sphere and all, we are going to derive after the
Gauss
Gauss
law.
law.
Yes,
Okay,
sir.
so now I want to discuss this electric field lines. Okay,
Yes, sir.
what are electric field lines? Electric field lines. Electric field lines or or the path traced by unit positive charge. Okay, it's an imaginary line which is actually the path traced by
Unit
a unit
positive.
positive charge. Say for
Yes,
example, I take a positive charge. Now if I put a positive charge here, then it will repel in this direction. So that is my electric field line.
yes,
If
sir.
I place a positive charge here, then it will move in this direction. If I place a positive charge here, then it will move in this direction. If I place a positive charge here, it will move in
Yes,
this direction. If I place positive charge here, it will move in this direction. If I place positive charge here, it will move in this direction. It will move in this direction. It will repel away.
yes,
So
sir.
it is a path traced by unit positive charge.
Yes, sir.
Okay. Now, if I take a negative charge, then let's see for negative charge. Now, if I take a negative charge, if I keep a positive charge here, then it
Attract.
attracts. So if I place here, it will attract. If I place here, then it will attract. If I
Yes,
place here, it will get attracted. Get attracted. Get attracted like this.
yes,
Okay.
sir.
Now you can see here. Now here the distance between the charge between the field lines is less. Here the distance between them is more.
More. Yes, sir.
Okay. Now let us take this as point as A, this point as B.
B.
Then I will say the electric field at A is greater than electric field at
B.
B.
Yes, sir.
Now, now here as this field here is greater and field here is less, that means I will say this field is non-uniform electric field. Is non-uniform
Electric field.
non-uniform electric field.
Field.
This is non-uniform electric field. Electric field at A is greater than electric field at
B.
B.
Yes, sir.
Okay, where the field lines are closer, there the electric field is more.
Greater. Yes, sir.
Yeah. Now, based on this, this is the concept. Based on this, he frame a question like this. Say, um, this is electric field line. Okay. This is a field line.
Yes, sir.
Now this point is, say this point is C.
Yes, sir.
This point is B. Okay. This point is
A.
A. Now you can see here the field lines are closer here.
Yes, sir.
So electric field at C is greater
Greater than
than electric field at A.
A. Yes, sir.
A is
Electric field at A.
A. Then
Greater
electric
than
field at
at
B is the least one
yes.
because the field lines are farther
Far.
apart.
Yes, sir.
Farther apart at B. Okay,
Yes.
so the questions are framed based on this concept like this. So if the field lines are closer, field lines are closer, field lines are
Closer.
closer. What does it mean?
More electric field.
Electric field is more.
Yes, sir.
Okay.
Yes.
Now let's say you have positive charge here and you have negative charge here. The field line, say the if you place a positive charge, it will move like this.
Yes, sir.
So now if you place a positive charge here, it will move like this. Place a positive charge, it will move like this. So the field lines will be like this. You can see here they were much closer,
Yes,
much
sir.
closer. So field is more. Okay. This is non-uniform
Magnetic field.
uh,
Electric field.
electric field.
Yes, sir.
The thing is, the field lines won't intersect.
Yes, sir.
Okay. Why it won't intersect? Because uh, the field direction. See, if you draw a tangent to this, that gives a direction of electric field at that point. If you want direction at a point, then you just
Yes,
draw
sir.
the tangent. Here, if you want electric field, you draw the tangent. That's the
Yes,
direction of electric field. Okay. E-
yes, sir.
Electric field lines never intersect. Never intersect. If they intersect, they will have two directions at the same point. So
Yes,
they'll
sir.
never intersect. Field lines never intersect. And this is also the a non-uniform electric field.
Electric field.
Non-uniform electric field.
Field.
Okay. Now
Yes,
this
sir.
is about the point charge. So when you place a point charge, then this is how the electric field lines are. Now, so if it is for a continuous body, say for example, you got a conductor and you have charges like this,
Yes,
then
sir.
this is continuous body, right? For the continuous
Yes,
body, see the if you place a positive charge here, it will move in this direction, in this direction, in this direction, in this direction, right? So now the field lines are equally spaced. So I call this as
uniform
uniform
electric field.
uniform electric field. Uniform
Electric field.
electric field.
Yes, sir.
It's uniform electric field.
Field.
Okay. Now you see
Yes, sir.
here, it is starting from positive and ending at negative. So
Negative.
it is again not coming back. You see only one direction. They are
Yes,
not
sir.
coming back. So they never form closed loops. The this electric field lines never form closed loops. Never form closed
Closed loops.
closed loops. Okay.
Yes,
So
sir.
this is uniform electric field.
Field.
Okay. Now, if you say like this, you have X and Y,
Yes, sir.
then electric field at X is greater than electric field
Electric
at
field at Y.
Y.
Yes,
Because
sir.
closer the electric field lines,
Closer
greater
the
the
electric field.
electric field. Okay,
Yes,
this
sir.
is non-uniform
Electric field.
electric field. Okay.
Yes, sir.
The electric field lines are perpendicular to the surface, say, and they don't travel inside a hollow space or something. Say now electric field lines are perpendicular. So we will
Yes, sir.
come this perpendicular to the surface.
Yes, sir.
Perpendicular to the surface. So here they will go perpendicular to the surface.
Yes, sir.
Okay.
Yes, sir.
Now when you place, they won't travel through the hollow space. Okay. They
Yes, sir.
always or perpendicular to the surface, and they don't travel through the hollow space. So this we call it as electrostatic shielding effect.
Shielding.
Electrostatic
Shielding
shielding
effect.
shielding effect.
Yes, sir.
Okay, so if you look at the watch will have a metal covering around it, right? A metal ring
Yes,
around it. So to protect it from the electric fields outside, the electric
yes,
fields cannot go into the
hollow space.
into the hollow part, hollow
Yes,
ring.
sir.
Okay,
Yes,
electric field will be equal to 0 here.
yes, sir.
Okay,
Yes, sir.
right.